Welcome everyone. In this piece of the lecture, our objective is to solve some examples to illustrate how to implement a self-tuning regulator. The first example is an example where we assume that we are going to cancel the process 0. So if we assume that we have a plant with the transfer function g, then the numerator would be the polynomial b, while the denominator will be a. Similarly, in the reference model, we'll have the numerator, we'll call it bm, denominator, we'll call it am. We will assume that the parameters of the plant are not known, so that means that b node, b1, a1, and a2 are unknown. And the parameters of the reference model are of course known, because these are parameters that we select so that the system the input-output relation would behave the way we like. Now there is an important note here. When we choose the reference model, the difference between the degree of the denominator polynomial am and the numerator polynomial bm, that has to be greater than or equal to the difference between the degree of the plant denominator a and the difference with the numerator polynomial b. The difference between the denominator and the numerator in a transfer function actually would give us the delay. And this simply says that you cannot really change the physical delay of the original system. So if a delay, if the system has a delay, say, of 1 or 2 samples, then the reference model should have similar or larger delay. And if you assume the opposite, like if you assume the difference between the degree of am and bm to be less than the degree of a and b, that would result in a non-causal controller. So this is actually a must, a condition that has to be satisfied always. Okay, now as I said, it is required to design a self-tuning regulator so that the process 0 is cancelled. Okay, let's recall that the b polynomial is the first order polynomial, the a polynomial is second order polynomial. So in the pawn placement design, we factorize b into two components, b plus, and this will contain the zeros to be cancelled, and b minus, and that factor will contain the zeros to be retained. Now since b is a first order polynomial, and we assume we know that, then b plus should be taken as q plus b1 over b node. Of course, we don't know b1 or b node. We'll see how to find them later on, but this is in general will be the form of b plus. And we said that b plus has to be monic, which means that since this is a first order polynomial, then the coefficient of q to the highest degree here, q to the power 1, the coefficient of q here has to be equal to 1. That's why we call it monic. Consequently, b minus will be just b node, a constant. Okay. Now once we do this, we can decide the degree of s and r. The degree of s is equal to the degree of r equal to the degree of a minus 1. The degree of a is 2, so this is 2 minus 1, and that will give me 1. So the degree of s equal to the degree of r equal to 1. We need to solve the Diophantine equation ar dash plus b minus s equals a naught am. We know that r is equal to r dash times b plus. Now we know that the degree of s is 1. We need to find the degree of r dash and the degree of a naught. The degree of r dash would be the degree of r minus the degree of b plus. Now we know that the degree of R is 1, the degree of B plus is 1, so that means that the degree of R dash will be equal to 0. The degree of A node should be equal to the degree of A plus the degree of R dash minus the degree of AM. So degree of A is 2, degree of R dash is 0, the degree of AM is 2, so that will lead to degree of A node equal to 0. That means that the observable polynomial A node could be just taken as a constant, and we typically take it equal to 1. So actually there is no need for an extra polynomial to represent A node. Now the next step is to solve the Diophantine equation. Now we substitute for A by q squared plus A1q plus A2. R dash has degree 0, so it is just a constant R node, plus B minus, which is B node, times S, and S is of degree 1, so I'm going to assume a polynomial for S, so I will take it as some constant S node times Q plus S1. So this is a first order polynomial to represent S. Now A node is 1, we assumed it to be equal to 1, and AM is the denominator of the reference model, so it is q squared plus a m1 cube plus am2, so I will substitute for that here, so it is q squared plus a m1 q plus am2. Now I have to solve this equation for the unknown parameters. The unknown parameters in this case would be R node, S node, and S1. I will do that by equating the coefficients of the same power of Q at both sides of the equation. So I have here the coefficient of Q squared would be R node. This is from the left hand side of the equation, and from the right hand side of the equation it is 1. So R node is equal to 1. Now I will do the same for the coefficient of Q. So I will get A1 R node plus B node S node equals to AM1. So this is the first equation. Of course R node is 1 from the previous solution. Second, I will take the absolute term, so I will have A2 R node plus B node S1 equals AM2. So if I do that, I can calculate actually the values of S node and S1. So I will get from the first equation S node equals AM1 minus A1 divided by B node, and S1 equals AM2 minus A2 over B node. So once I calculate the value of R node, S node, and S1, I can actually write expressions for the S and the R polynomials. We know that R is equal to R dash times B plus, so that would be equal to Q plus B1 over B node, so this is R, and S would be equal to, as we have assumed it, S node Q, so S node is AM1 minus A1 over B node times Q plus AM2 minus A2 over B node, so this is S, I still have to calculate the polynomial t, and as we know, t is equal to bm times a node divided by b minus. So that would be bm node q divided by p node. So once I get r, s, and t, the ball placement design is complete. It is possible to write the control law as a polynomial r times the control signal equals to the polynomial t times the set point minus the polynomial s times the feedback signal y. Now if you substitute for the polynomials r, t, and s, we can derive an expression for the control signal u of t to be implemented. So let us do this. R is just q plus b1 over b node times u of t, and that would be equal to t, which is bm node over b node times q times the set point uc, minus s is am1 minus a1 over b node times q, plus am2 minus a2 over b node times y of t. Now in order to get an expression for u of t, I will just multiply both sides of the equation by q to the minus 1. So that will give me on the left hand side u of t equals, and then I will move this term to the right hand side of the equation, so it will be b1 over b node times ut minus 1 plus bm node over b node times uc of t minus am1 minus am1 minus a1 over b node, that would be multiplying y of t, minus am2 minus a2 over b node multiplying ut minus 1. So this would be the control law, and if we know the actual values of the plant parameters, we can just substitute for this, and the closed loop system will act as the reference model. However, we don't know the values of b1, b node, a1, and a2, and that's why we need to do parameter estimation and use the self-tuning regulator. Anyway, in order to find these values, I have to put the plant in the normal form. So I have to write an expression for y of t as phi transpose, which is the regressor, times the unknown parameters. I get this from the original equation of the system. We know that y over u is equal to b node q plus b1 over q squared plus a1 q plus a2. In order to find an expression for y of t, I will multiply the numerator and the denominator by q to the minus 2. So I get up here b node q to the minus 1 plus b1 q to the minus 2 over 1 plus a1 q to the minus 1 plus a2 q to the minus 2. Now I can write an expression for y of t. It would be the vector minus y t minus 1 minus y t minus 2 u of t minus 1 ut minus 2. This multiplies the theta vector, and the theta vector would be composed of the unknown parameters a1, a2, b node, and b1. So this is the regressor, and this is the parameter vector. So now we can implement the self-tuning regulator algorithm. So let's see the algorithm. The first step is to actually initialize the recursive least square using some initial values for the parameters and the corresponding covariance matrix P of 0. So this is the first step. The second step, at sample t, we first measure the output of the system. We construct the regressor, and then we execute the recursive least squares algorithm to find the estimate of the parameters. And finally, we calculate the control signal u of t. Of course, to calculate the control signal, we are going to use this expression of u of t that we have derived. However, we are going to depend on the estimated parameters, so b1 hat, b node hat, b node hat, a1 hat, b node hat, and b node hat, and a2 hat. We notice here in the control law that we divide by b node. That means that we have to make sure that we don't initialize the value of b node to be 0, and we have to ensure through our calculations that it will also not take a value equal to 0 in order for the control law calculations to be feasible. Now, once we do that, this will complete the calculation of the control signal. We will wait for the second sample. So at sample t plus 1, next sample, we go back to step number 2, and we repeat the sequence once again. So this is the algorithm to implement the self-tuning regulator, assuming that we cancel the process 0. The second example that I'm going to consider is an example where the process 0 is not cancelled. So let us assume a second order system with unknown parameters b node, b1, a1, and a2, and assume that we are given the required poles of the reference model in the form of the polynomial am. Also, we are required to achieve unity DC gain for the reference model. That means that if we have a constant input, reference input to the reference model at steady state, the output should exactly match the input or the set point. So let's assume that the reference model would be given by bm over am. We have agreed before that bm should include the zeros of the process that will be retained, and some other factor, I will call it Bm bar. Now since here we are not going to cancel the process 0, we know that the process 0 is given by B node Q plus B1. That means I can take this equal to B minus, and consequently B plus will be just equal to 1. Now in order to achieve a unity DC gain, we require the limit as Q goes to 1 of Gm of 1 to be equal 1. So if we substitute, if we calculate, let me first write an expression for Gm. It is B node Q plus B1 over Q squared plus AM1Q plus AM2, and that multiplies Bm bar. Now to achieve this condition of a unity DC gain, it's enough to take Bm bar as a constant. So if we substitute then for Q by 1, we get B node plus B1 over 1 plus AM1 plus AM2 times Bm bar is equal to 1. This achieves unity DC gain, and consequently I can calculate the value of Bm bar as 1 plus AM1 plus AM2 over B node plus B1. So this will be the expression for Bm bar. Now to continue, we have to solve the Diophantine equation. AR plus BS equals A node times AM. Remember here R is equal to R dash because P plus was taken equal to 1. We are not cancelling any of the process zeros, so that's why R appears in the equation to be solved. We take the degree of R equals the degree of S equals the degree of A minus 1. So that means the degree of R and S will be equal to 1. We can also calculate the degree of the observer polynomial. It will be equal to the degree of A plus the degree of R minus the degree of AM. Now this is 2, this is 2, and this is 1. So you will end up with degree of the observer polynomial equal to 1. That means that we have to choose a first order polynomial to represent the observer. Now one simple choice is to just take, let's write in terms of Q, just to take the observer polynomial equal to Q, which means that we put root at the origin. Now the effect of that, first of all, since the roots of A node will appear in the closed loop poles of the system, it means that this is a fast pole that will not affect the dynamics of the overall system, because the dominant poles will be then those of AM. So this is from the transient response point of view. However, if the system happens to have some noise, the choice of A node with very fast poles like that make the system very sensitive to noise. However, in our example here, we are assuming just a deterministic system, and that will not affect us much, so we can do this. Now we have to solve the Diophantine equation for the polynomials R and S. So I'm going to substitute for A here by Q squared plus A1Q plus A2 times a first order polynomial for R, let's say R naught Q plus R1 plus the B polynomial, which is B node times Q plus B1, times a first order polynomial for S, that would be S node Q plus S1. That's equal to A node AM. We have already selected A node to be equal to Q, so Q times the desired factor AM, and that is given to be Q squared plus AM1 Q plus AM2. So now what we are going to do is to equate the coefficients of similar power of Q at both sides of the equation and find a set of equation that can be solved to find the unknown values R node, R1, S node, and S1. So let's do this. If we take the coefficient of Q cubed, we will get R node equal 1. If we take the coefficients of Q squared, we will get R1 plus A1 R node plus B node S node equals AM1. Coefficients of Q will get A2 R node plus R1 A1 plus B1 S node plus B node S1, that's equal to AM2. And finally the coefficient of the absolute term, it would be A2 R1 plus B1 S1 equal to 0. So these are the set of equations that have to be solved. We know that R node is equal to 1, so we don't have to bother with that. And we can write this in a matrix vector form to find R1, S node, and S1. So we can write this matrix times R1, S node, and S1. And this is equal to some vector here. So the first equation, which comes from the coefficients of Q squared, we'll have here 1 times R1 and B node times S node and 0, and this is equal to AM1 minus A1. Second equation, which comes from here, that would be A1 times R1 B1 and B node, and that should be equal to AM2 minus A2. And finally A2 times R1, here we have 0, and B1 times S1, that will be equal to 0. Actually, the structure of this matrix seems to take some pattern. You can notice that, and it's called Sylvester matrix. There are some programs actually to construct such a matrix, which typically appears when we solve the Diophantine equation. Anyway, if we do that, we can calculate the value of R1 S node and S1 just by multiplying from the left by the inverse of this matrix. So if we do this, we will be able to find the polynomial R and S. Now we can write an expression for the polynomial T as Bm A node divided by B, as we agreed that B is a factor in Bm, so that will lead to Bm bar times A node, so that will be equal to 1 plus am1 plus am2 divided by b node plus b1 times q. So once we find the polynomials t, r, and s, we can actually implement the control law. Now let us write an algorithm to implement the proposed self-tuning regulator. The first step is to initialize the recursive least square algorithm, and that's by the selection of the initial estimate of the parameters and the initial covariance matrix. The second step is to consider at the current time t, we measure the output, we form the regressor, we execute the recursive least square algorithm to calculate the estimate theta. Then we solve the Diophantine equation this is the Diophantine equation that we have to solve. Let's call the equation number 1. So we solve this equation to find the coefficients of r and s. And then we compute the control signal u of t. At the next sample, we go back to step 2 and repeat whatever we have done before.